One of the most basic questions that we often want to ask is, why are we spending so much time on linear independence? And what good is this concept of being able to determine whether one vector is a linear combination or a function of the other vectors? Well, it actually does tell us something about the span of the vectors in the first place. So just a couple of bits of intuition here. Whenever we look at two vectors, for example, 1, 0, and 5, 0. So these are linearly dependent because I can write 5, 0 as a linear combination of the other vectors. In this case, it's just one vector, but it's going to be 5 times the 1, 0 vector. In other words, I could make it to this location in 2 dimensions, 5, 0. If this is 5, 0, then the way I can make it there is by taking 5 multiples of the 1, 0 vector to that point. And so that will get me there. Now, what this also tells us is that really my span of these vectors is really just where one of these can take us. Since I can get to the other one with the first, or vice versa, I could take 1/5 of 5, 0 and get 1, 0. This tells me that basically I'm only able to generate vectors that are along that horizontal axis. What this also means is that if these were vectors that were part of an A matrix, 1, 0, 5, 0, times x, y, and let's just say I wanted to make it to some other location. Let's say that there's a location here, 3, 17, that I want to be able to make it to. So effectively, I'm going to be solving this system of equations right here. 1x plus 5y equals 13, or 3, and 0x plus 0y equals 17. So that poses a major dilemma already because 1, 5, 3, 0, 0, 17, we see that this is not possible. This is saying 0 equals 17. There's just nothing that I could scale these second components by here in order to produce that value of 17. So it tells me basically about whether I'm going to have unique solutions or potentially infinitely many solutions. If you have n vectors in n dimensions that are linearly independent, so here we had two I'll give you an example of two linearly independent vectors in R2. And I'm going to use the most intuitive ones that will kind of show you right off the bat. These are called the standard basis vectors. And where I can get to with these two vectors is one of them will allow me to travel horizontally, and the other one will allow me to travel vertically. So 0, 1, and 1, 0 are these two vectors respectively. And so clearly if I want to make it here, then I just take my pink vector out far enough this way and my green vector far enough up to make it to that point. So if I want to generate any other vector, like 3, 17, then I'm just going to scale the 1, 0 vector by 3, and I'm going to scale the 0, 1 vector by 17, and then add them together. So linearly independent vectors, specifically if I have two linearly independent vectors in R2, that allows me to guarantee that I'm going to have a unique solution. So this will have a unique solution to AX equals B for any B. For any B. But if I change those vectors back to what we had up here, 1, 0, and 5, 0, this system right here will only have a solution for some. AX equals B may have solutions for some B, some vectors B, but the solution is not going to be unique. If you can find a solution. And why I'm saying that is, first of all, if, for instance, I want to take 1, 0, 5, 0, and I want to make it to a location in 2 dimensions like 0, 10. Well, I'm not going to be able to do that. So that's just out of the question because I have 0 equals 10. I don't have any y components here that will allow me to actually travel up and down. But this one says, hey, get me to the point 0, 10, which is way up here. Now, it will have solutions to some vectors. For example, let's say that we want to use these two, determine their coefficients, add them together tip to tail to make it to, we'll say, 10, 0. Well, there's lots of ways you could do that with 1, 0, and 5, 0. In fact, infinitely many ways. One such way would be to take 5 times 1, 0 plus 1 times 5, 0, which is the same thing as taking 10 times 1, 0 plus 0 times 0, 1. And you could do this all day long. So that's what the consequence is going to be if you have fewer linearly independent vectors than you do dimensions. In this case, we only have one linearly independent vector, and that's going to be the 1, 0. Now, similar kind of thing holds for R3. Let's say we have 3 linearly independent vectors in R3. Okay, so the easiest ones that we can really think of are going to be the 1, 0, 0, 0, 1, 0, and 0, 0, 1 vectors, because what they allow us to do is to travel in the 3 different directions, but component-wise one at a time. So there's the 1, 0, 0 vector. 0, 1, 0 vector points this way, so that allows me to travel in the y direction, and the third vector here is going to allow me to travel in the z direction, which is 0, 0, 1. So that will allow me to get off the xy plane. So if I have 3 linearly independent vectors in R3, this means that we're going to have unique solutions to ax equals b for all, or for any vector that you can find. There's no vector that you can give me that I cannot travel to uniquely with these 3 vectors. So, for instance, let's just say, hypothetically speaking, that we have some point out here, and we'll just say that this point up here is the point 7, 22, and 13. Well, I could just take 7 times this one to get me to the correct x position, 22 times this one, 13 times this one, and if I add them together, boom, we've got ourselves we've got our problem solved. This one will allow me to come out this way. The blue one, the blue vector will allow me to traverse this way, and then the green one will get me to my final destination, which is that point right there. Now, if you have fewer linearly independent vectors than you do dimensions, for example, if I only have 2 linearly independent vectors in R3, for example, it could be like this, where I have 1, 0, 0, 0, 1, 0, and maybe I have another vector, but it's just not going to be linearly independent. It's going to be linearly dependent on the other 2. So for instance, if I pick 12, 14, 0, then if I take 12 times the first plus 14 times the second, then I can generate the third. And by all means, I'm not saying we're deleting this one, but this one just doesn't give us any additional information that the first 2 already give us. And so you can see that in this case, for these 2 vectors, 1, 0, 0 and 0, 1, 0, as before, 1, 0, 0 allows me to travel in the x direction, or backwards into the negative. The 0, 1, 0 vector allows me to travel in the y direction, or in the negative y direction, which means that I can make it to any point that I want that's inside of the xy plane, or perhaps in the negative x, negative y plane, or negative x, positive y, positive x, negative y. I can make it to anywhere in those xy planes. I can't get off the ground. I can't make it upwards. So in this case, we can say ax equals b may have a non-unique, and perhaps it could be unique. I shouldn't say non-unique because there's only one way to combine 1, 0, 0 and 0, 1, 0, but we're also taking into account the third vector. So if 1, 0, 0 and 0, 1, 0 allow me to make it to any point along this, then I'll be able to get back home to the origin with the 12, 4, 0 vector. So for example, if I took 12 times this plus 14 times this, and I took -1 times this, that would allow me to get, out here to 12, 14, 0, and then this vector would allow me to make my way back to the origin. So may have a non-unique solution for some b that for some b where b is equal to some multiple. We'll just say that this is a c0. So I can make it to any location where there's an x and y component, but where there's a 0z component. And now if I extended this to n dimensions, so if I have n linearly independent vectors in Rn, then Ax equals b will have a unique solution for any b. And the reason this becomes important is because systems that have linearly dependent vectors, the mathematics can actually become a little bit more challenging to execute. So we like linear independence. It doesn't always happen, but we need to make this distinction because systems that have linearly dependent vectors will not have certain attributes. When we start studying properties of matrix algebra and knowing whether A is square and has linearly independent columns will tell us a lot about what features it will have. Namely, what this will imply is that A has an inverse matrix called A -1, or A inverse. It's not A, the components of A raised to the -1, it's just called that, A inverse. And that's what basically this will allow us to establish. If this is not a true statement, if you have fewer than n linearly independent vectors in Rn, then your span of those vectors is going to be some subportion of that dimension. Just like up here, we could only span the xy plane.